Okay, we just saw the recursive solution for the towers of Hanoi. It was actually conceptually very straightforward, and if you write the program, you see that's simple as well. Um, but there's recursion involved, and we saw that every time a lot of function calls as well, and every time you call a function, we saw what happens on the activation stack, and so there's a lot of overhead whenever you do these function calls. And over here, since there's, as we saw, it's probably exponential, so there'll be a lot of exponential placements and displacements from the activation stack. So the question is there a non-recursive solution? In other words, can we find some kind of iterative way to do this? That's what we're going to look at right now. And it turns out that there is. It's conceptually very, very simple. And it turns out to be pretty nice to code as well. Okay, so that's what we're going to look at right now. So as before, we want to go from tower A to tower B. And we want to do it iteratively, right? No recursion, no function calls at all. So what we need to do is we need to define something called a candidate. Right, a candidate. The candidate is going to be the ring that we're going to be moving, right? The candidate. So what do we mean by the candidate? So first of all, let's make some definitions. We're going to say that the following definition. We're going to say that a ring, like these rings are 1, 2, 3, a ring is available if it is on top of a tower, right? In other words, an available ring is one that can possibly be moved. So in this case here, what's the available ring, right? Just one, right? Because 2 and 3 are on top of the tower, right? So that's an example of an available ring, right? That's the first definition. Okay, and then what is a candidate, right? So a second definition, a ring is a candidate by candidate means we can possibly move him if, number one, he is available, right? It is available. In other words, I could reach it. And number two, it is the smallest available ring that we did not move, that we did not just move on the previous step, right? Because the algorithm goes step by step, right? So we're going to move a ring, move a ring, move a ring. So all the time what we're going to do is we're going to be moving a candidate, right? That's what we're going to be moving. And how do we know it's a candidate? First of all, it has to be on top of a tower. And then it has to be, of all the ones on top of the tower, it has to be the smallest one that we did not just move, right? So that's the example. So first of all, over here, there's only one candidate right now. That's the one, right? And so that's the definitions. And now, how does the algorithm work? All right, so let me get rid of these definitions and check the algorithm. So the algorithm is going to be stated in terms of the candidates. So the algorithm is very straightforward. We want to go from tower A to tower B, right? That's the idea. So here's how it works. First of all, we got to check if there's work to do, right? Is there still work to do, right? So if all the rings are on tower B, then just stop. Right? You're done, right? Well, that's not the case over here, right? Because there is they're nothing on tower B, right? Okay, so that's not the case. So then what you do is, the second step is locate the candidate. So right now we have a candidate. This guy's the candidate. And the third step is now going to be move the candidate to the right to the first legal tower. What do I mean legal tower? You know, the same legal tower we meant before. Legal meaning that when you end up putting it there, you're not putting it on a ring that is smaller than it, right? So first of all, you're going to check to see if you're ready to stop. If not, you're going to locate the candidate. Then you're going to move the candidate, and then our old friend, the go-to statement, go to step 1. Right, now let's see if you're finished and so on. So it's a trivial algorithm, right? So in this case, let's actually do this, right? So we go like this. First question: Are all the rings on tower B? No, there's nothing on tower B. Okay, step 2: locate the candidate. Okay, I've located the candidate. Okay, why is that the candidate? Because it's the smallest one that's available, because there's nothing anyplace else. It's available because it's on top of the tower, and we didn't move it in the previous step because there's no previous step. This is the first one. Okay, so I located the candidate. Now, move the candidate to the right to the first legal tower. So let me pick it up. I want to move it to the right. Now, can I put it over here? Can I put it on B? Absolutely, right? Because that's a legal tower. We haven't put anything on it before, so one is, in fact, smaller than anything on there. Okay, so now go to step 3. I go to step 4. Step 4 says go back to step 1. Let's go to step 1. Are all the rings on tower B? No, they're not, right? Locate the candidate. So let's check out what's the possible candidate here. So the candidate has to be available. Who's available? Well, who's available here? So clearly 1 is available, right? There's 1, and 2 is available. But what is the smallest one, right, that hasn't been moved? Well, so 1 is the smallest. 1 is smaller than 2, but we just moved 1. So 1 is not a candidate, right? Even though it's an available ring and it's smaller than the 2, but since we just moved it, we can't move it again, not right now, right? So my candidate is going to be this one here, right? So I'm going to move it to the first available, first legal tower. So what is a legal tower here? Can I move it here? Can I put a 2 there? Absolutely not, because the 2 is bigger than the 1. But I can move it over to tower C, so I can put it here on tower C. Okay? Step 4, go back to step 1. Are all the rings on tower B? No, they're not. So locate the candidate. So if you look at it, we have 3 possible, three available rings. But which is the smallest one that has not been moved? Well, it's 1 again, right? Because 1 is smaller than the other ones, and we didn't just move 1. We just moved number 2. So 1 is my candidate. I pick up number 1, and I move it to the right to the first available, to the first legal one, and I put over here. This is pretty cool. Look, it actually did it the same way as the other one, right? It's very nice. Okay, now go back to step 1. Are all the rings on B? No, they're not. I hope you're counting along with me, see how many steps this takes. They're not. Step 1 says, are they all on tower B? The answer is no. Locate the candidate. So what is the candidate? What's the candidate? 3 is on top, right? That's a potential. 1 is on top. But we can't move 1 now because even though 1 is smaller than 3, we just moved 1. So a candidate over here is going to be 3. So we pick up 3 and we move it to the first available space. What's that? We move it to the right. We put 3 over here. Okay? Okay, back to step 1. Is everything on B? No, it's not, right? So locate the candidate. What are the candidate? What's available here? So 3 is available and 1 is available. And 1 is actually smaller than 3, right? But that's no good because we just moved 3, right? So what's the candidate? The candidate is number 1. So we're going to move the candidate to the first available space. Well, let's move him. Okay, so we move him to the right. Where are we going to move him to? He's going to fall off, right? So what move to the right means move around in a circle, right? Imagine it's a circle here to the first available place. So what's the first available place? if we treat this thing as a circle, so the first available place is going to be right over here. So I'm going to take the 1, and I'm going to move the 1 and put it right over there. Okay, so that works. Okay, so now back to the top. Have all the rings, are they on tower B? They're not. Who is my candidate? Who's my candidate? So who's available, right? Who's available? So all 3 of them are available. What's the smallest one we didn't just move? So we just moved the 1, so 1 is not a candidate, right? 1 is not a candidate. And 2 is smaller than 3, so 2 is my candidate. I pick up 2, and I move him to the first available space. Again, I want to move to the right. There is no right, so again, we go around the circle. So we go around the circle to the first available. Now, can I put him down over here? I can't, because 2 is bigger than 1. So I have to keep going, and I can put over there, right? So when I say move to the right, locate the first legal tower. 1 is not a legal tower because I end up putting a 2 on a 1. So there's a 3 over there. So I pick up the 2, and I put it on top of here. This is a really neat algorithm. Notice it's completely iterative. So the 2 goes on over here. And now who's my candidate? Well, there's only 2 guys on top. There's the 1, and then there's the 2. The smaller one is the 1, and I didn't just move the 1. Right? I just moved 2 on the previous move. So I pick up the 1, and I put him on top, and that's it. And I come back to step 1. Are all the rings on tower B? The answer is yes. So I am done. Okay, and here we have 1, 2, and 3 on tower B. So notice there's no recursive calls. In fact, there's no function at all. It's just a loop, and you keep going around and around and around until it's done. If you've been counting along, you will notice that the number of times that we move things is exactly 7, right? And if you do the analysis here, you'll see that it's just as before. It's going to be 2 to the n minus 1, where n is the number of rings, right? So even though the number of moves is going to be the same, but the amount of work that it does is going to be less because there's no function calls. And what we'll be talking about in the last couple of classes is what the overhead is for function calls. There's none of that, and we get the same result. So this is very, very nice. Okay, before we move on, though, I just want to just do 2 things. I want you to try this yourselves. Okay, so pause the video, and let's put 1, 2, and 3 back on here. And then just see if you can recreate what we do, basically going through this algorithm, right? And counting the steps as you go along. Make sure you understand exactly how it works. Okay, so pause the video now and go. Okay, I hope that worked. I want to try it one more time. And I'm sure you got the 7 steps, right? So let's try one more time, but now instead of with 3, we're going to just try it with 2. So we saw before if there are 2, if n is equal to 2, so we saw it's 2 to the n minus 1, so 2 squared is 4, and 4 minus 1, that should give us 3 steps, right? Before we had 7 steps, because we had 3 rings, now we should have 3 steps. So let's make sure we understand how this thing works. So let's do it. So who's the candidate, right? So who's the candidate? The candidate is 1. Let's pick up 1 and move the candidate to the first available ring. Okay, so that's 1 move. Who's the candidate now? 2 is the candidate. Well, I can't put the candidate there. I move it over here. So there's the candidate. That's move number 2. Who's the candidate? The candidate's going to be 1. So we pick up the 1 and we move it over here. There's a problem. There's a problem. The problem is we've used up all three moves, but we're not on tower B. Now there's another problem. Who's the candidate? So let's see. There's nobody over here, so no candidate there. Nobody over here. How about 1? Is 1 a candidate? Well, it's the smallest ring, but it's not the small, and it's available. It's on top, but it's not the smallest ring that we just did not move because we just moved them. So it doesn't work. It was such a great algorithm, but it doesn't work. What is one to do? What is one to do? So let's do the following thing. I want you to, what did it work? It worked for the case that n is equal to 3, right? Then it worked. But when n is equal to 2, it didn't work. So first of all, what you want to do is ask the following question. I mean, this is a number and this is a number. What's the difference between 3 and 2? Right? That's question number 1. And question number 2 is, can you amend this algorithm somehow? You know, the idea seemed to be nice, right? It worked for 3. Can you amend the algorithm in some way so that we can actually salvage it? So please pause the video and see if you can come up with something. And maybe we didn't just waste our time, because maybe we can really save this thing. Okay, so let's work on this thing together. So this didn't work, right? 2 didn't work. But let's see if we can salvage this. We have 1 and 2 over here. So first of all, what's the difference between 1 and 2? Well, yeah, it's a big difference. 2 and 3. 2 is 2 and 3 is bigger. But there's another difference, right? 3 is an odd number. I think you might have come up with this yourselves. And 2 is an even number. So how about we do the following thing? Before we start the algorithm, we check to see if we have an even number or an odd number. The algorithm that we saw worked for odds. It worked for 3. If you do it for 5 and 7 and so on, you see it worked also. And so what we did is we located it and we moved to the right. But what happens if it's an even number and instead of moving to the right, let's see if we can move to the left. Let's see if that makes any difference whatsoever. Let's try it. The same algorithm, right? So are all the rings, still we want to go to tower B, right? Are we finished? We're not finished. So step number 2, locate the candidate, right? Who's the candidate? The candidate's number 1. So now what we're going to do is we're going to move to the left to the first available. So we move to the left, of course, we're going to fall off, but we saw before we go in a circle. So what's the first available one? Well, there's nothing over here. So tower C is the first available one. Let's pick it up and put it down, right? So that's step number 1. We did 1 step. What is the candidate? Well, there are 2 values on top. There's the 1, but we just moved them. So the candidate is 2. And again, we're moving to the left. So pick up the candidate and move it to the first available tower. Which is the first available tower? Well, I'm going around in a circle. This one is not available because there's a 1 on there and the 2 is bigger than the 1. This one is available. So we pick it up, right? Let's get rid of that. Pick it up and move it. There's a 1 here. Move it here. That's move number 2. Who is the candidate? Well, we have a 1 and a 2. We just moved the 2. That's the candidate. Pick up the candidate, move it to the left to the first available one, and plunk it down there, and this is available. I mean, that's a legal one. And in fact, we just did 3 moves, right? 2 squared minus 1, it's equal to 3. And there it is, it's on tower B. So we managed to fix this up, right? And all we need is generalize a little bit. The first, we need a 0th step, right? A 0th step. And the 0th step says, check to see if it's even or odd, and then depending on even or odd, we decide what we're going to put over here, right? That's the thing that has to change. So if it's even, we're going to move to the right, and if it's odd, we're going to move to the left. So we have this really nice algorithm. All right, so now, of course, we want to write a program to do this. So we have the algorithm, we have to decide on a representation. How do we represent these towers? We need a data structure, some representation, because only after we decide that, only decide how do we represent the towers, how do we represent the candidates, can we begin to manipulate those things in an actual program. So that's going to be the next thing to do. So how about, what do we have to represent? Like the 3, right? The 3 towers, right? So how about some kind of 2-dimensional array? I don't know, right? 2-dimensional array. And we'll put the, let's say we have 3, this will represent tower A. This is going to be 1, 2, 3, 4, 5. I don't know, and this is, I don't know, I'm not sure what to do here. So let's say this is going to represent my tower A, and that's going to be my tower B, and tower C. Let's say put a 1, 2, 3 over here, and then I have to let's call this thing, I don't know, towers, right? The array is going to be towers, and it's going to be how many rows? Let's see, 1, 2, 3, 4, 5 rows. How many columns? By 3, and then we'd have to keep track of where the top is going to be. So let's say we have a one-dimensional array here called top, right? And so this is 0, 1, 2, 3, 4. So in this case, we're going to start top with 1. And then what? And then what's the top of this guy? So I don't know, let's say, I don't know, -1, -1. And then how do I find out who the candidate is? So I guess I go through the various, I go tower sub I sub j. I'm not going to go through this because you realize this is pretty messy. Of course you could do it this way, but this is really not the way to do this. This is not the way to do this. There's a much, much, much better way, and it has to do with something in C++, an available data type that we have not yet seen, but it's really a very nice, powerful, and easy to use data type. And that's what we're going to look at right now, and it is called a vector. So let's take a look at what vectors are in C++. What are vectors? So vectors are very nice things. It's basically an array, except you can do much more with it. You access it like an array. In other words, you can use brackets on it and so on, but it has a lot more powers. It's like a super-powered array. So for example, a regular array can't grow, right? You have to say in the beginning how big the array is. Vectors can grow. You can't put something in the middle of an array and have every, sort of, and using your elbows move things to the side. You can't do that to vectors. You can't find out what the size of an array is. The size of an array is given. It can't change. So, in the main program we saw how to do that in class. But if you pass an array to a function, remember all you're passing is the pointer to the beginning of the array. So in the function, you have no way of finding out how big the thing is, right? You can do that with a vector, right? So vectors are really, really nice things. So you can, first of all, you might go just simply on the web and check out vectors. So for example, we can do something like this. And you can get some very interesting examples and all the details. But we're going to just look at a couple of them, and certainly we'll be able to get enough information to write the program that we want. So first of all, an important thing to note is that vectors are examples of something called templates in C++. We haven't seen those yet. We'll see those at the end of the semester. But basically, it's a data structure where the type has to be at this point. Let's just imagine it's a strange notation, right? We'll get into the reasons for this later on. So basically, what happens is I want to create a vector. Think vector. Think this array of integers. So what I need to do is I need to say I have a vector, right? I say the word vector, and then I say vector of what? So if I say vector of integers, I put int in here. That's the data type. It's going to give me a vector of integers. Okay. If I say instead of vector of integers, I say vector float, right? If instead of int here I say float, it's going to give me a vector of floating point numbers, right? So over here, this is the template parameter, whatever that means. But I can basically, when I say a vector, it turns out that there's no such thing as a vector. It's a vector of some type. In the same way, if you have an array, I also have to say, if I have an array of integers, I have to say A is an array of integers. I have to say what it is. An array of floats, I can't just simply say, give me an array A. I have to say an array of what? It's the same thing over here with a vector, okay? But now here's interesting. Can I create an empty array? I know I have to tell how big the array is when I start. With vectors, I can. I can say how big the vector is, and I can say I want an empty vector. So if I say vector int, and I simply give the name of the array, that creates an empty vector for the vector. It creates an empty vector for me. And how do I put elements into this vector? Well, we'll see. Now, if I want a vector of particular size to be the equivalent of saying I have an array of size 3, so what I do is I say the name of the vector, and then in parentheses I put how big I want the vector to be. right? So this is vector 2, v2, is going to have 3 spaces, 4 integers, right? Now, as opposed to arrays, these vectors will be initialized to whatever the 0 of the type is. So integers, the 0 is the 0. If it would be float, the type would 0.0, right? What about this? Another way of creating vectors. This also gives me a vector of size 3, but I have an initialization. The second argument is the initialization, and the initial all being initialized to 0 and to 10, and that's the way to do this. And likewise, how about something like this? I have a vector this way. Remember, we saw this universal initializer notation. So this gives me a vector. This is no longer, these aren't the dimensions anymore, right? This tells me the size was 3. This tells me when I say v4 and 3 and 10, so it's actually the values in the array, right? Before, the 3 over here, right? In this example here, this 3 told me how it's like a one-dimensional. All these vectors are one-dimensional vectors. This tells me how many elements, and this 10 is the initialization. Here with the bracket, this is just a list of all the elements. So this is going to be a vector of integers, right? The size is 2. How do I know the size is 2? Because there's only 2 elements in there, and the values in the vector are 3 and 10. Now, just like in an array, it's like an array in the sense that I can also use the bracket on it, and just as an array, the indices start at 0. Likewise, in the array, in the vector, it starts at 0 also, right? So we can use the bracket. We can use the bracket to index into a vector, but you can't. For example, if I would just simply say what we set up here, that I have vector v1, it's an empty vector, so I can't even go. I can't go v1 sub 0, because if it's empty, there's not even a 0th element, right? So I have to be careful when I use the brackets that I'm actually indexing into a position that exists, right? Make sure that the indexed position exists. So as we just saw, what if v1 sub 0 does not exist? But what about if I say v3 sub 1? So v3, that has 3 elements, right? That's v3 up here, 3 elements each of 10. So I can actually say v3 sub 1. What is v3 sub 1 going to look like, right? Well, what does v3 look like? So this is v3. This is v3. And we have a 10 in here, and a 10 in here, and a 10 in here. And this is v3 sub 0, sub 1, sub 2. So v3 sub 1 is the second element in the vector. Okay? So what did we see until now? Till now we saw that we can actually declare these guys, and we can use them just like an array, but we saw additional features here, right? We can create an empty one, and we have an easy way of giving initial values, right? Okay, so what else can we do? Well, here's a very interesting thing we can do, and this you cannot do with vectors. You can do a pushback on a vector, right? So what happens is, if the vector starts with n elements, whatever n is, let's say even if it's 0 elements, if I say pushback on that vector, then it's going to add an element to the back of the vector. So for example, if we have the vector v1, which was initially empty, and I say push back, and I have this for loop, so I goes 1, 2, 3. So what's going to happen is when I is equal to 1, what is 10 times 1? 10 times 1 is 10. It's going to push back. So here I say, here I have the element that I want to push back. The vector start at, there was nothing in there. So the first thing that happens is it pushes a 10 in here. I becomes 2. 10 times 2 is 20. It pushes a 20 onto a vector with 1 element. And now there's a 20 here. So the vector now has 2 elements. And it does a pushback again. It comes back here. I becomes 3. 3 times 10 is 30. It does a pushback again. So now the vector has 3 elements, right? So this is a very nice thing. I can make the vector grow as the program runs. Try to do that with your array. And there's another thing I can do. I can access the back. of the array, right? So I can say, take my V1 that now has a 10 and a 20 and a 30, and I can pop the elements off. I can get rid of them. So if I say, for example, now notice there's nothing in there, right? When you use the pop back, you don't pass an argument in there, but it needs the brackets just to indicate that this is a function, right? So what that's going to do is it's going to pop it off, right? Remember we talked about a stack? I have a stack. I can push on the stack. I can push on the stack. I can push on the stack. The stack's going to grow. We can actually use a vector to represent the stack. So it was empty, then we put a 10, and we put a 20, we put a 30. And this here is the top of the stack. It's the back of the vector, really, right? And so now if I say, tell me what's on the back, well, if I say pop back, what pop back is going to do is just going to get rid of the top element. So if my vector now looks like this, if V1 looks like this, and if I say V1 pop back, what's going to happen is the 30 will disappear. It doesn't give it to you, right? And this is going to be the new top. It's just going to get rid of it, right? What if I need that element? I want to get it off the vector, but I need it. So I can also say back. So what back does, it returns, but does not remove the back element of the vector. So therefore, if you think about it, let's go back to the case where I had 3 elements in my vector with 10, 20, and 30, right? 10, 20, and 30. So just like I have here, this is the back element. If I want it, I could say I have some integer I, right? Let me say some integer k, and I say, what am I going to put in k? I'm going to say go to v1 and do a back, right? Call the back function. So what's the back function going to do? Here's my k, right? What the back function is going to do is going to go to v1, which is this thing here, right? It's going to look at the back, and it's going to take the back element, which is the 30, and it's going to store it in there. Is it going to remove it? No, back does not remove it, right? Back does not remove it. It just tells you what it is. But if I want to get rid of it, so now I can say go to v1, right? Go back to my vector v1, and then what? And then call the function pop underscore back, and we saw, and with the parentheses, we saw pop back just removes, doesn't return. Now I want you to just understand this. We haven't seen this notation before. The notation is important, right? This is what we haven't seen before, the dot operator, right? So you give the name of the vector, v1, and then you put a dot, and let's say you call pop back, right? Pop underscore back. So the way that you use it is you have the name of the vector and the dot, and what this means, we'll see later on when we look at classes and structs, we'll see where this came from, but this means on this object, on the v1 vector, I want you to apply the function pop back. So you do it by saying first the name of the vector, and then say this, and this means on v1, call or apply the pop back function. It's the same thing, all of them, right? This had a dot, and this had a dot, and likewise the pushback also, this had a dot over there. So it says on the vector v1, I want you to apply the function pushback, and I want you to push on the back of v1 that 10. Okay, so what did we see exactly? So now at this point we know how to declare these vectors, right? Remember, it's not just vector itself. You have to say vector of what, right? In this case, we put in the brackets vector of integer, give it a name, say v1. We could, if we wanted to, we could give it initial values, as we saw, the size and so on. And we saw 3 operations on vectors. We saw the pushback operation, we saw the popback operation, and we saw the back operation. And what we want to do now is we want to see if in some sense we can use a vector and the operation on vectors to implement our non-recursive towers of Hanoi. Now, if you just stop the video for a moment and think about this, why would this even be an idea? Well, if the towers are represented by these vectors, and I can say, show me what's at the back, if I do this well, if I do this correctly, what's going to be at the back is going to be the top element, right, of a stack, of a tower, right? If I do a pushback, 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 and I have, let's say, pushback a 3 and a 2 and a 1, we'll just do this in a moment, the 1 is going to be on top, that's going to be the last one I put on, that's going to be the back. So when I say, tell me what's at the back, that's going to be the top of my tower. This is going to work out nicely. Think about this before, pause the video, think about this, and we're going to go on and just take a look how this will actually work when we code. So here's what we're going to do. We're going to have an array, right? We're going to have an array over here. And it's going to be, the array is going to be t. It's going to be called t sub 0, t sub 1, t sub 2. Now let's say I want an array of integers, right, of size 3. So I say I have an integer array, the name of the array is t, and it's of size 3, right? What if I want an array not of integers of size t, if I want bools? So I say I have an array, everything here is a bool, and the array of size t. If I want it to be a floats, I say I want it to be a floats of size t. But what I want to put in here, I want to put vectors in here. So I want an array of size 3, but I want every element of this vector, of this array of size, I want it to be a vector of integers. So I say vector int, let me write it a little bit better, right? I want a vector int, and then I say t3. So what does that mean? That means this one, t sub 0, is going to be a vector. Right? There's going to be a vector in here. T sub 1 is going to be a vector. There's going to be a vector here. And this is going to be a vector. What's originally going to be in there? What is t sub 0? Well, remember we said vector int, we said v1. It was empty, right? So initially, if all I say is that these vectors, I have an array of 3 vectors, so t0 is going to be an empty vector, nothing in there. t1 is going to be an empty vector. t2 is going to be an empty vector, okay? But I can put stuff on there. If I push, let's say I push a 3 and a 2 and a 1, so I'm going to push a 3 and then a 2 and then a 1. And if I say show me the top, well, we'll actually go through it and see, right? So, but eventually, initially, these all start as empty vectors. And so we're going to represent, this is going to represent my tower A, and that's going to represent my tower B, and that's going to represent my tower C. It's a very, very nice idea here, right? Because I don't have to keep track, like we saw with the 2-dimensional array, which I did not go into because it's super messy, and that's really not the way to do this. I'd have to keep track myself of where the top of the various towers are. Here I can just query the vector. If I want to go to vector 1, right, the vector called t1, and I say vector t1, who's at the top of the vector, right? So that's going to be t1, right, vector t1, right, t sub 1 dot back, right? That's going to tell me vector t1 is this vector over here, and back is going to tell me what element it is. So that's the way I can tell who's at the top of that tower. If I want to get rid of it, I can say what? I can say t1 dot what? Pop underscore back. And whatever is on the top of this thing, right? Let's say I have 4, 3, 2, 1, let's say. So I say pop back, that's the back, right? Pop back means get rid of that. So you see right away, this gives us a very, very neat way of manipulating these towers. And it's exactly the right tool. That's what's so nice about this, right? If you have the wrong data structure, it's like very difficult, very messy, very easy to get wrong. But here, if you have the right data structure, it becomes very, very easy to manipulate and very easy to think about, right? So let's see if we can see how this thing works, right? So I have this vector t sub 0, t sub 1, t sub 2. They represent my different towers, and let's see how we're going to make this work. So we're going to do this now. We'll see what happens for odd, for n odd, right? N is going to be some kind of odd number, like, for example, 3, right? So that means we're going to be moving to the right, as we saw. So, okay, so the first thing I do is I pound include IO stream, and in order to use vectors, you have to put this in your program. You have to say pound include vector, and it's going to let us, number one, create vectors so that the compiler knows what a vector is. And second of all, it's going to let us manipulate it by using all those functions that we saw. And there are many, many other functions too, right? I can ask the size of a vector, for example. I didn't see that one, but I can ask the size of a vector. So, for example, what was the algorithm that we just looked at, right? How did we know that it was time to stop. So if n is equal to 3, let's say, we can ask if the tower has 3 elements. In this case, we're going to put an extra element in there for technical reasons, which we'll see. But I can ask if the size is what I'm expecting for a full tower. And if it is, then I know to stop. So let's actually go through the program. So the first thing we do is I have to make sure I include all the appropriate things. And then let's get going. So first thing I'm going to do is I'm going to initialize the vectors. And I'm going to do it like this, right? So what's going to look like is this. Here's my t sub 0, t sub 1, t sub 2. And I'm going to say, well, I'm going to go to t sub 0, right? Go to t sub 0 and do pushback of I. I'm going to do this just for 3 towers, right? I mean, it's always 3 towers, but I'm going to do this. Well, let's say n is going to be 3 in this case, right? N is the number of rings, right? So what I'm going to do is I'm going to go for I starting at, so if n is 3, the number of rings is 3, I'm going to start at 4. And I'm going to go 4, 3, 2, 1. I'm going to go back, right? So I'm going to go to t sub 0. That's this one right here. And I'm going to push back I. So I'm going to push back first a 4, and then a 3, and a 2, and a 1, right? And then I'm going to go to t sub 1 and t sub 2 and push back n plus 1. So if n is equal to 3, n plus 1 is 4. So my initialization puts a 4 in every element of the, so these are all vectors, right? T sub 0 is a vector, t sub 1 is a vector, and t sub 2 is a vector. So I already put my initializations, push the following values in here. I'm going to start with 4, 4, and 4. So these are no longer empty vectors. And on my initial tower, I'm going to put 1, 2, 3 on top of that 4, right? Now, why am I starting with a 4? Because this way, 4, if n is equal to 3, right, then the number on the bottom, this 4, is always going to be bigger than either 1, 2, or 3, obviously. So I'm never going to be able to, when I push things onto a tower, I don't have to test if the tower is empty, because they're never going to be empty. And any of the elements from 1 to 3 are always going to be smaller than the 4. So it's gonna save technical. You'll see this. It saves tests as we go through, right? So if I want to have 3 rings, then I'm gonna put n plus 1 on there, and then when I test to see if I'm finished, I'm gonna say, do I have all 4 rings, right? 1, 2, and 3. Are they all, and 4? Are they all on tower T1? Okay, let's see what happens. So this was the initialization. Now, remember how the algorithm works, right? So here is, let's see the program. Here's what the program. So you might want to look through it first, and then we're going to go through it, right? First, try to read through it. There's obviously things that are missing here. We'll put it, but it fits on one page, basically, beside the initialization. Okay? So look and see if you can see what's going on here, and then we'll do this thing together. Okay, so we did the initializations, and we need a from tower and a to tower and a candidate. So we start with a from tower 0, that's where I'm moving to. The to tower is going to be 1, because we have odd, if we have an odd a number of rings, the to tower is going to be 1. And the candidate is going to be on the top of tower 0, of T0, and I know it's going to be 1 because I'm starting out with 1, 2, 3, 4, whatever n is going to be, right? So what we're going to do here is we're going to first, as we go through this thing, it's a while loop, and as long as I am not done, right? As long as I'm not done. So what are we saying? We're saying here n is equal to 3. So when we're finished, what are we going to see on tower 1? What are we going to see on tower 1? When we're done, we're going to see a 1, a 2, and a 3, and a 4, right? Because n is equal to 3, we're putting that 4 down there for whatever technical reason you'll see as we go along. So when it's all done, tower 1, the middle tower, is going to have 4 values. As long as it doesn't have 4 values, then we still have work to do, right? So in this case, n is equal to 3, n plus 1 is 4. So as I go through, I can say I have some vector v. I can ask the size of vector v, right? It's going to tell me how many elements there are over here. So since n is 3, n plus 1 is 4, so I say, let me check t sub 1, let me check its size, right? If the size is not equal to 4, then I'm not done, right? Because I don't have a situation where all the elements are already on there. So as long as that's the case, I'm going to still go through my algorithm. That's the equivalent of step 1 when we looked at the pseudocode, right? Is everything on B, right? The way we say that in code is this. This is the way that we say is everything on B. If this is not clear, please listen to it again. Stop the video, listen to it again. So we did the initialization, and we know that we're not finished. So what we're going to do is we're going to write out, just like we did with the recursive version, we're going to say like this, move number, whatever. We're going to keep track of the number of moves. So that's going to be, we've initialized move earlier on, so move starts at 0, plus move says 1, so it's going to say move 1, and we're going to print the following string. Transfer the candidate. What's the candidate? Transfer ring number 1 from tower char from 65 to tower from char from 65 from plus 65 to tower 2 plus 65. So if you actually wrote the first program that you were assigned this semester, this should not come as a shock. What does this mean? What does this mean? So we saw that the ASCII values there's integer values, right? And so what is the from here is 0, right? From is 0. So what is 0 plus 65? Well, that's 65. But what happens when I say char of 65? What's the ASCII that's assigned, that's associated with 65? It's A. So, right, the character A. So this is going to say transferring candidate from tower. In this case, it's going to say from 0. So say from tower A to tower. It's going to string. What's it going to be? Of 2 plus 65. But what is 2? We started with 2 equal to 1. What's 1 plus 65? Right, 1 plus 65 is 66. What is char of 66? Char of 66 is the character B. So this is going to print out the first time around. Remember, we're dealing with an odd number of rings. It's going to say move ring number 1 from tower A to tower B, right? That's what's going to happen at the very beginning. Now, we're going to start moving the rings around. We want to move the rings around. How do we do that? Take a look at this. Even though it's not finished, we want to find out something. We want to find the new from tower. We want to find the new to tower. We want to find the candidate, right? So we want to fix these things. And then we're going to come back up to the top. So we're going to have a value from, a value for to, a value for candidate. We'll come back up to the top of the while. So then we can print it out again, right? We come back up to the top, and we can use the from and the to and the candidate to actually write out the next move. And then we're going to come back over here, find out the from and the to and the candidate, come back up to the top, and so on and so forth until tower 1, right, the middle tower representing A, has all the rings on it. So just take a look at this for a moment. Look at this code, so you can figure out how can we figure out the from, how do we figure out the to, and then how do we get the candidate, right? And then we will actually work through this a bit. So what did we just do? What did we just do? We printed out, move the top ring from tower 0 to tower 1, right? We printed that out. And now, so this is the from tower over here, right? We said the from tower is from tower 0, and the to tower is tower 1. So once we print it out, we have to actually change the state of the system. What we really need to do is we need to take the top, we're going to do these two steps right over here. We want to take the top of tower from and push it. There's a 4 over here and a 4 over here from the initializations. And we want to take that and we want to push this over here, so there'll be a 1 there. and then we got to pop it off of here, right? We got to get rid of it. So we have to push the top of the from tower, right? The from tower, we want to take that. We want to bring it onto there. We want to push it onto tower 2, and then we got to remove it from the from tower, right? So how do we do that? Using what we said before, pause the video and see if you can figure it out. So how do I take this and put it here? So basically what I want to do is I want to go to tower from, right? I say go to tower from. How do I say tower from? Tower T sub from, right? Go T sub from, that's this tower over here. And I want to do what with T sub from? I want to find out what's at the top, right? So let me just move it over a second. I'm going to go T sub from, right? And I want to say what's at the back of that. That should give me the 1. So I'm going to say dot back, right? The function. So that's going to give me the 1. What do I want to do with that 1? I want to go to push it on to the top of tower 2, right? So I'm going to take this, right? This is the 1 over there. And I'm going to do a pushback onto tower 1. So I'm going to say, I'm to tower 1, right? So I'm going to say go to tower sub 2, right? Tower sub 2, which is this guy. And on there, I'm going to do a pushback dot push underscore back of this value, right? So it's T sub 2 dot pushback, right? I'm going to go T sub 2 pushback. I'm going to put something over here. What am I going to do that? What's on top of the from tower? So that is going to put a 1 over here. This is a really beautiful construction, right? So the argument to the pushback is going to be the T sub from dot back. That's the 1 over here. And I'm pushing it onto tower 2, and that's going to do this. But now there's one more step. I've got to remove it from here. I got to get rid of this on top. So what am I going to do? I'm going to do a pop back on what? I'm going to say go to tower from, right? T sub from, right? That's this tower over here, dot pop underscore back. And there he goes, right? So this is a 2-step process. And what does this 2-step process accomplish? It accomplishes these 2 things, right? So now I change the state, and the state looks like this. 1 is on tower 2, and 2 and 3 are over here. So now what do I want to do? I want to get ready to do the next step, right? So the next step is I have to figure out what my candidate is, and I want to figure out what my from tower is and what my to tower is, right? So we've already accomplished the changing of the state. What we did up here was we printed, right? We did a print over here, and then we did what we said we printed, and we moved the 1 over here. Okay, so this is the situation that we have right now. So now this is my to tower right here. This is my to tower. I want to know what the from tower is going to be, and I want to know. So let's see, what could the from? I want to know what the new from tower is going to be, right? What's my new from tower? What's my new from tower? Could it be the current tower T? Could it be the current tower T? In other words, could the one that we have over here, could that be my new candidate? And the answer is no. Can't be my candidate, right? The current to tower cannot be the front tower. Why is that? Because the candidate has to be the one, can't be the one I just moved. So I'm going to move something to tower 2, right? Move something to tower T. So whatever I put on tower T, that can't be the candidate because I just put it there. So it has to be, it can't be in this case tower, it can't be tower 1. It has to be either tower 2 or tower 0. Does that make sense? You have to make sure it's very, very clear. So when I want to find the new from tower, it cannot be whatever the current to tower is, right? So how do I do that? If now T is equal to 1, right? This is 1. If T is equal to 1, so it's either going to be this one or it's going to be this one, right? It's going to be one of those 2. So which one is it going to be? Well, first of all, it's going to be either tower 2 or tower 0. So an interesting thing is to think about how do I even say that? How do I even say that? Think about, how do I say, given t, how do I know what the other two towers are? Just stop and think about it for a moment. So this is my current 2 tower, right? 2, right? 2 is equal to 1. That's the tower number. So it's either going to be where? It's either going to be, say, 2 plus 1 or 2 plus 2, right? It's going to be this one, right? This guy here, or that one, right? So if 2 is equal to 1, 2 plus 1, that's 2. That's going to be this guy. But 2 plus 2 is going to be 3. But there is no tower. There's no tower 3. There's tower 0, 1, and 2. So how do I do it? I really need it to go around. And the answer is, think for a moment, how do I go around? So what I really want to look at is, I'm going to look at 2 plus 1 and 2 plus 2, and I want to go to that tower. So it's going to be tower this or tower that, but what? I want 2 plus 2 in this case is going to be 3. So I really want to do this mod 3. Right? I want to do this thing mod 3, and I want to do this thing here also mod 3. Right? Why? Well, let's just check it out. Why do I want to do it mod 3? Well, what is, remember, 2 is 1 in this case. What is 1 plus 1? Right? So 1 plus 1 is 2. What's the remainder of 2 when I divide it by 3? Right? What's the remainder? The remainder is what? It's 2, right? So dividing, giving the mod 3 over here just leaves it at 2. But what about 2 plus 2? 2 is 1. 1 plus 2 is 3. What is 3 mod 3? What's the remainder when I, remember the mod gives you the remainder. What's the remainder when I divide 3 by 3? It's going to be 0. So therefore, that's exactly what I need here. So let me go around the circle. So 2 plus 1 mod 3 is going to take me to this one. I'm going to be looking at t sub that. And when I say 2 plus 1, 2 plus 2 mod 3, that's going to take me to this one. So let's see, just make sure we understand how that works in all cases, right? So let's say, for example, that my 2 tower was tower 0. Let's see, it works in all the cases. So 0 plus 1 mod 3 takes me here. That's fine. 0 plus 2 mod 3 takes me here. That's fine. Let's say my 2 tower was this one. That's the one we're looking at now. So so 1 plus 1 mod 3 takes me to this one. That's fine. 1 plus 2 mod 3 takes me to this one. What about the 2 tower is this one? So where does t plus 1 take me? Mod 3. So 2 plus 1 mod 3 takes me here. That's good. And 2 plus 2 mod 3, that takes me here, and that's also good, right? So that's the way we're going to find out where the other possibilities are for the next from tower. Make sure we're clear about what's going on. Make sure it's clear what's going on. What I'm trying to figure out is, given I know where I just placed the ring, I placed it on tower 2. So what I want to know now is, where can I find the candidate, right? So the candidate can't be on the 2 tower because I just put something on the 2 tower. It has to be either on the 2 plus 1 tower mod 3 or the 2 plus 2 tower mod 3, right? So which one is it going to be? Which one's it going to be? It's going to be the one of these that has the smallest value, right? Because the candidate is going to be, I have to look at the possible tops, and I need to take, and I haven't just moved from this one. I have moved this one because these are not the 2, right? That's not the 2 tower. So the smaller of these is the one that has the candidate. Think about that for a moment. So I'm over here in the code, and I want to know what my new from tower is going to be. So I need to put a test, right? I need to put a test in here, right? Right in here, it's got to come a test. So let's take a look at the diagram, right? This is my 2 tower, so the candidate is not going to be here. It's going to be either in this one, 2 plus 1, or 2 plus 2. So which one's it going to be? Well, what's the top? What's at the top of 2 plus 1? That's a 4. What's at the top of 2 plus 2? Well, that's going to be a 2. So which is smaller, the 2 or the 4? Clearly, it's going to be the 2. So my new from tower, where I'm moving from, is going to be that one, which is this one, right? Tower 0. So how do I write that in code? How do I say that? How do I say that? Again, stop the video and see if you can say that. I want to look at the tower 2 plus 1 mod 3 and 2 plus 2 mod 3, and the one that has the smaller value on top, that's the tower that's going to be the new from tower, because that's where the candidate is. How do you say that in code using these vectors? Stop the video and try to write it out. So I want to find the new from tower, right? The new, where am I moving from? So if I want to look at these two towers, this one, and find which one has a smaller value. Well, how do I find out the values on those towers? That is going to be the back, right? So if T sub 2 plus 1, right, mod 3, right, 2 plus 1 mod 3, if what's at the top of how do I set up the top of that? In other words, I say, tell me what's at the back, right? So if this value here, right, that's the top of 2 plus 1. Where is 2 plus 1? On the diagram we had, 2 plus 1 is this one. This is 2. This is 2 plus 1. If the value of 2 plus 1 dot back is less than the value and the back of T sub 2 plus 2 mod 3, right? If it's less than dot back, right? If that's the case, right? This is my if statement, right? This is my if statement from here to here, right? I check this is the top of what? This is the top of 1 to my right, and this is the top of the 1, 2 to my right. So if the top of the 1 to my right is smaller than the one that's 2 to my right, then the new from tower, right? Then the new from tower is going to be the 1 to my right, right? So the new from tower is going to be, which one? Is going to be what? How do I say that? I want it to be, remember, I need the value either 0, I need the value, this is my 2 tower, it's going to be the 2 or a 1. So how do I say that? It's going to be 2 plus 1 mod 3. That's going to give me this one. But otherwise, right? Otherwise, the top of my tower directly next to me is not less than the 1 2 away. So the 1 2 away has the smaller value, and so then the from is going to be 2 plus 2 mod 3. Right? That's going to be the new from tower. Does that make sense? If it doesn't, please listen to this thing again. It's using these the functions that we get from the vector, and it's once you get a whole the hang of how this thing works is really very, very elegant, right? So again, just understand the concept on a high level. I know that I want to find the new from tower, right? The new from tower cannot be the current 2, because on the current 2 is where I just moved the ring to. So it's either going to be 1 to my right, right? It's going to be 1 to my right, or it's going to be 2 to my right. So how do I know which one? So I check the value on the top, which is the back function, the back of the tower 1 to my right, and I check it against the value 2 to my right. If the top, if the value on the top of tower 1 to my right is smaller, so that's where the candidate's going to be, that's going to move from. So the from tower is going to be 2 plus 1 mod 3. Otherwise, it's the other one, and it's going to be that. Okay? Make sure that that's clear. So now I know where I'm going to be moving from, right? It's one of those, either the one or 2, to the right, going around the circle, of course, to the right of the current 2 tower. So at this point, we've already taken care of this, right? We know what the new from tower is going to be. Now I need to know what my 2 tower is going to be. So what is my 2 tower going to be? Well, it certainly can't be the from tower, right? So it's either going to be the one immediately to the right of the from tower or 2 to the right of the from tower. It's the same kind of idea. Which one is it going to be? Stop the video and see if you can figure it out. Which one is it going to be? So we figured out which is my next from tower, right? We figured out that it's going to be this one, right? Figured it's going to be this one. So now what I want to know is which is my 2 tower, right? To say that this is the new from tower, it means that I'm going to be moving this one either to here or to here, right? So how do I figure it out, right? If this is my from tower, I can't be moving it to the new from tower. So my 2 tower is going to be either from plus 1, just like we saw before, from plus 2, but of course we have to mod that by 3, right? Just like we did before. It has to be modded by 3. Why do we have to mod it by 3? Because we could end up, right, we could be ending up, you know, the new from tower could be one of the other ones. So we have to go around the circle. So how do I know which one? Could it be this one? Is it possible that it's this one? The answer, of course not, right? Because I'm going to be moving the 2, and the number 2, the 2 is on the top. That's the disk on top. I can't move it here because 2 would be bigger than the 1, right? So the way that I figure out what my new 2 tower is going to be is I compare the top of my new from tower to the top of the other 2. And it has to go on one of those, but it has to go on the one which is going to be a larger number than this, right? So in other words, I'm going to be looking at, since this is my new from tower, I'm going to look at the top of T sub from, right? I'm going to go T sub from, right? T sub from, in this case, the from is going to be 1. We figured that out already. Dot back, and that's going to be the 2. And I'm going to compare the value there, right, this 2, to the value at the back of this one and this one, right? In other words, the back of T sub from plus 1 mod 3 and T sub from plus 2 mod 3. And I've got to pick the one. It's similar to this. Obviously not the same, but it's similar to the one we just saw before. And I'm going to pick the new 2 tower to be the one such that the value on top of it is going to be larger than the 2, right? I'm not going to write the code. I'm going to leave that to you to write. But that's basically the idea. The same thing as we just saw, but you have to use these functions. So when we finish with that, when you write the thing correctly, we're going to now have what's going to be the next 2 tower. And finally, we get the candidate. What's the candidate going to be? Well, the candidate's going to be the one on top of the from tower. So it's going to be the from tower dot back, right? T sub from dot back. And then what do we do afterwards? We come back all the way over here to the top of the while loop, and we're ready to print again, right? And then we print. We go through all of this. And how much do we do? How many times do we do this? We do this until the top, as long as the while loop is not satisfied. The condition of the while. What is the condition on the while loop? The condition of the while loop we saw earlier is that the number of elements, right? T sub 1, which is my tower B, right? As long as the size of it is less than, in this case, 4, that means we haven't completed because I don't have 1, 2, 3, and 4 on that tower. And that's the idea. It's very straightforward. And so I'm going to actually, this is going to be your assignment. And the assignment will consist of 2 parts. Number one, make sure this works for an odd number. You have to just finish this. Here is the, 85, 90% of the code. You've got to write the stuff that goes in here based on what we did, and then make sure that it works for odd. And then, of course, you're going to have to make it work both for odd and even. So you're going to have to take this program, right? Here's a main program. And essentially, at the beginning of the main program, you're going to ask, give me the value of n, how many rings there are. And then you're going to see if n is even or odd. If n is odd, we're going to move in that direction. And that's what this program does. And you just have to do the modification. If it's even, you're going to move in that direction. But always in the while loop, what's going to terminate it is if all the elements, if n plus 1 elements are on tower B. And that is how this works. And this is a very beautiful data structure, this vector, and very powerful and very useful.